Now we're ready for Newton's third law. And Newton's third law, in some ways, I think is the most fun because it's at least it was to me the least intuitive of all the laws. But once you really kind of understand it, a lot of things start to make sense. So Newton's third law essentially says, actually I can tell you kind of what you might have heard. You know, a lot of people say every action has an equal and opposite reaction. Another way of thinking about it is if there's an object and it exerts a force on another object. So let's say I have let me think of something. Let's say that I have a fist. So let me draw the fist. So I have a fist, and it is punching someone's face. So this is the face, and they're not happy. Right? And let's say this fist is punching the face with a force of, I don't know, 10 newtons. Let's not make it so violent. Let's say that this is a hand massaging the face. It's pressing upon the face with a force of 10 newtons. So what Newton's third law tells us is that the face is also, I guess we could say, punching the hand, or, well, no, we're not using the violent. The face is also pressing upon the hand with a force of 10 newtons in the opposite direction, but along the same, I guess you could say it along the same line. So does that make any sense? Because it seems like the hand is doing something to the face and not the other way around. But if you think about it, when you press on someone's face, their face might kind of press in a little bit, but you also feel something on your fist or on your hand. I mean, think of it. Maybe a better example would be, instead of someone's face, imagine if it was a tree that you've decided to massage, or I guess punch. So here is the tree. That is the tree. And the same thing would happen. If you were to press upon the tree if you were to punch the tree, essentially, the tree is essentially punching back with the exact same force. And here it makes sense because your hand will hurt. And maybe in this case the face will hurt because the face kind of gives way while your fist doesn't. But here the tree is not giving way and your fist will. Another way to think about it is and this is probably the least intuitive. If I have the earth, and here am I standing on top of the earth. So we already figured out that the pull of the earth, or the force of gravity upon me, it's pulling down upon me at 150 pounds. That's the force. And we could say it in Newton, but pounds is a unit of force, it's weight. But it also, Newton's third law tells us that I'm actually, at the same moment, pulling on the earth with a force of 150 pounds. And this might not make a lot of sense to you, but you could think about it this way. When I'm stepping on, let's say I'm stepping on a soft surface like sand or something, I feel my feet will compress a little bit, but so does the sand, probably by, depending on which one's softer. And another way to think about it also is if me and the earth are both in deep space, right? And I am, you could say, falling towards the earth because the earth is pulling on me. How do we know that the earth isn't falling towards me? I mean, it's kind of arbitrary. There's no frame of reference. We're both in deep space. There's nothing else to look at. We're essentially falling towards each other. I'm not necessarily falling to the earth. The earth's not necessarily falling to me. We're just falling towards each other. And that's another way of thinking about this. So you can think about every example where a force applies to something. And if you really think about it, the force is going the other way as well. For example, if I were to take a bat to this tree. So if I were to take a bat to this tree and swing on it really hard, so I were to swing on this tree really hard, I have a good chance of breaking that bat. Even though you would have thought, hey, that bat is applying the force to the tree. Well, why is the bat breaking? Because the tree is applying an equal force to the bat. And actually, if I did it perfectly, if I had let's say I had two bats or two swords, and for some reason I think I'm going a little too violent with these examples, but I guess we're talking about forces, so maybe violence is justified here. But let's say I have two swords that are completely identical hitting each other, right? And at some point, and let's say I keep increasing the force at which they're kind of going in opposite directions. At some point, they're going to break, right? If I just keep increasing the force on, one guy swinging in one direction, one guy swinging in the exact opposite direction, and the force just keeps increasing, at some point they're going to break. And you could say that, well, this guy says, well, I was the only guy swinging because this guy was stationary, and the other guy would say, well, I was the only guy swinging because this guy was stationary. But at some point, not one of them is going to break; they're both going to break, because even though this mauve sword was pushing on this blue sword with some force, the blue sword was essentially pushing back with the exact same force. So if these are completely identical swords, at some point they're going to break. Another way we could think about it, one of the swords could have just been held, stationary. It could have been held stationary by somebody. And this other sword, that if you were to press down on it and kept increasing the force with which you press, at some point they both would break, because when they're identical. If one was harder than the other, then that would stick around. Hopefully that gives you a little intuition. I mean, we could do a bunch of more examples. I'm trying to think. Oh, well, let me think of another one, a less violent one. Let's say we're in deep space again, and I have a basketball. Let me do it in orange. I have a basketball, and it weighs 1 kilogram. And let's say that I weigh 50 kilograms. So let's say I push. So my hand pushes on this ball with a force of, let's say I push on that ball with a force of 10 newtons. 10 newtons to the right. What this tells me, what Newton's third law tells me, is that essentially that basketball is going to push on my hand with an equal and opposite force. So it's going to push on me with a force of 10 newtons. So what's going to happen? So we're touching. I'm pushing on 10 newtons on the basketball, and we're in deep space. There's no gravity from random stars, etc., etc. And then the basketball is going to push on me with the force of 10 newtons simultaneously. So the basketball, we know that F equals ma. So the basketball, so 10 newtons is equal to 1 kilogram times acceleration. So acceleration is going to be 10 meters per second squared to the right. So as long as we're touching, the basketball is going to accelerate at 10 meters per second squared to the right. And simultaneously, I'm going to accelerate at a certain acceleration to the left. And what's that going to be? Whoops, I'm 50 kilograms. So we know that the force to the left is also going to be 10 newtons, and that equals 50 kilograms times acceleration. So here, the acceleration is going to be 1/5 meters per second squared. So when I push on, so we're both in deep space floating around, and I push on this 1 kilogram basketball with a force of 10 newtons, it's going, as long as I'm pushing on it, it's going to accelerate at 10 meters per second squared, as long as I'm pushing on it. But simultaneously, while I'm pushing on it, it's exerting an equal and opposite force of me on 10 newtons. So I'm going to actually move back a little bit at a slower acceleration, and that's just because I have more mass, at 1/5 meters per second squared. Another example you could think of is if someone shoots a gun, right? There's that, I forgot the term because I don't shoot guns, but when that your shoulder jerks back, as I've seen in the movies, when a bullet is shot. And that's because the gun is exerting a force on that bullet, and the bullet is exerting an equal and opposite force on the gun, and which kind of pushes back on your shoulder. And the reason why the bullet just goes a lot faster forward than you and the gun go backwards is because your mass is much larger than the bullet. Hopefully that gives you a little bit of intuition on Newton's third law. And this is kind of non-intuitive. So look around you in the world, look at all the forces that are being applied, and I want you to think about, when one force is being applied in one direction, why does it make sense that another force, an equal and opposite force, is being applied in the exact opposite direction? I'll see y'all.